In this video, we're going to derive an equation which gives us the pressure as a function of depth in a liquid. The derivation we're going to do in this video builds on concepts covered in the previous video. So if you have not watched the previous video yet, where I went through these ideas conceptually, I'd encourage you to watch that first and then join this video for the derivation. In this video, we're going to be using the idea of pressure in a fluid. Pressure is defined as the force that the fluid exerts on some surface divided by the area of the surface. We're also going to be using the idea of density, which is the ratio of a substance mass to the volume it occupies. So anyway, let's say that we have a tank of liquid here. We will say that the pressure at the top surface of the tank, where the tank presumably meets the air or some other fluid, is P0. We're going to say that this tank is filled with a liquid of constant density. So rho will denote that constant density. You can see that from the larger liquid, I have marked out a column of that same liquid with area A and depth H. And we want to figure out what is the pressure at the bottom of that column. We're going to start by drawing a force diagram. And this will look a lot like what I did in the previous video. So here's our force diagram. At the top surface, I have a force from the atmospheric pressure pushing down on the liquid. So let me call that F atmospheric. Then you have the gravitational force, which is to say the Earth is pulling down on that liquid column. Let's just call that gravitational force G vector as usual. And then we have the liquid down here pushing up on that bottom surface of the column. Let's call that force there F liquid. Now let's go through, as we usually do, and put in expressions for the magnitudes of these forces. We can use here that the force associated with the pressure is pressure times area. So at this top surface here, we have pressure P0. So the magnitude of this force would be P0 times the area of that surface. The magnitude of the gravitational force, we will say as usual, is the mass of the liquid column, then times little g. And then we have this force here. This is the force of the liquid just below the column, pushing up on the bottom of the column. This force also arises from a pressure. So we will solve for force in this formula and write the magnitude of this force as P liquid times the area. Now we can proceed as usual. I'm going to put in a coordinate axis. I'm going to have a y-axis pointing up. Then, as we usually do, we can set up a table into which we're going to enter the y components of the force vectors. So first, I will just list the force vectors along the top. We have gravitational force vector, force from the atmosphere pushing down, force from the liquid below pushing up. And for each of those, we want a y component. All right, y-axis points up, so y component of the gravitational force would be minus mg. Y component of that force from atmospheric pressure would be minus P0A. And y component of that pressure force from the liquid would be P liquid times A. Since our assumption here is that the liquid column is static, we can say that the sum of the y components of the forces on the liquid column is 0. So we're just going to sum these to 0. Before we proceed, I'd like to play around with the mass of the liquid column a bit. Remember that the density of some piece of material is equal to the mass of that piece divided by the volume it occupies. So if you look at the mass of the liquid column that appears right there, we can say that that is the density of the liquid times the volume occupied by that column. All right, what would be the volume of this column? Well, the area of that top square is A and the depth is H. So the volume would be A times H. So the mass of that entire column would be the density times that area A times the depth H. So now let's take this expression and put it into our force balance. We then get, for our force balance, minus rho AH G minus P0A plus P liquid times A equals 0. Now let's divide through by area. All those areas cancel. And then let's just solve for P liquid. We then get P liquid equals P0 plus rho GH. We now have an expression which gives us the pressure in the liquid as a function of the depth H beneath the top surface of that liquid. If we like, it might even be nicer to write P liquid as a function of H equals pressure at the top surface plus density of the liquid times free fall acceleration times our depth in the liquid. So we can see then that the pressure at a depth H beneath the surface equals pressure at the surface plus density of liquid times free fall acceleration multiplied by the depth beneath the surface. Notice that this expression only works if we assume that the density of the liquid is constant. However, this is generally a pretty good assumption. And in this class, any liquid we look at, we're going to assume that the density is constant. So in the next video, we're going to do an example problem which uses this formula.